In 1949, a mathematician handed Albert Einstein a birthday present. It was not a bottle of wine. It was not a card. It was a proof, 4 pages long, published in the Reviews of Modern Physics, Volume 21, Number 3, pages 447 through 450. And what those 4 pages proved, using Einstein's own equations, the exact same field equations that describe the curvature of spacetime around every star and planet and black hole in the observable universe, was that time is not real, not relative, not strange, not counterintuitive, not real. The passage of time, the flow from past to present to future, the thing you feel right now as you sit there and the seconds tick forward, is not a feature of the universe. It is a feature of you, an artifact of your perspective, a hallucination baked so deeply into human experience that nobody thought to check whether the equations actually supported it. Somebody finally checked. The equations do not support it. And the man who checked handed the result to the man whose equations they were on his 70th birthday in front of every major physicist alive. And then the physics community did something remarkable. They looked at the proof, confirmed the math was valid, and never spoke about it again. The man who wrote those 4 pages was Gödel. If you have heard that name before, it is probably because of something he did 18 years earlier, in 1931, when he was 25 years old and decided to destroy the foundations of mathematics. He succeeded. His incompleteness theorems proved that any consistent formal system complex enough to describe basic arithmetic contains true statements that the system cannot prove. Mathematics, in other words, cannot fully verify itself. The implications of this were immediate and shattering. David Hilbert, the most influential mathematician of the early 20th century, had spent decades building a program to place all of mathematics on a firm axiomatic foundation, to prove that every mathematical truth could be derived from a finite set of axioms, that mathematics was complete, consistent, and decidable. Hilbert believed this with the fervor of a prophet. On September the 7th, 1930, he delivered his retirement address at a conference in Königsberg, the city of Kant. It ended with the most famous rallying cry in the history of mathematics. Wir müssen wissen. Wir werden wissen. We must know. We will know. Those words were later inscribed on his gravestone. They remain there today, a monument to a dream that died the day before it was carved. But the day before that speech, at a round table at the same conference, a quiet 24-year-old Austrian had stood up and announced, almost as an aside, that he had proved Hilbert's program impossible. Almost nobody in the audience understood what he had just said. One person did. John von Neumann pulled Gödel aside after the talk. He grasped the significance immediately. Within weeks, von Neumann had independently worked out a corollary, the second incompleteness theorem, and wrote to Gödel about it on November 20th, 1930. But Gödel had already submitted his manuscript to Monatshefte für Mathematik on November 17th, 3 days earlier. Von Neumann graciously did not raise priority issues. His reaction to the implications was blunt. It is all over. He meant Hilbert's dream. He later wrote that Gödel was absolutely irreplaceable, the only mathematician alive about whom he would dare make such a statement. He called the incompleteness theorem singular and monumental, a landmark that will remain visible far in space and time. That was 1931. Gödel had just ended the dream that mathematics could be complete and self-contained. 18 years later, he would do the same thing to time. And the parallel between the two results is not superficial. In both cases, Gödel found something hidden inside a formal structure that the structure's architects never intended and could never remove. Hilbert designed his axiomatic program to capture all mathematical truth within a finite set of rules. Gödel showed that mathematical truth overflows any such set. There are always truths that the system can state but cannot prove. The system is incomplete, not because of a failure of cleverness, but because of a feature of reality. Mathematical truth exists independently of our formal frameworks and will always exceed them. Einstein designed general relativity to describe the geometry of space-time, the curvature produced by mass and energy, the trajectories of planets and photons and galaxies. He built time into the framework as a dimension, a coordinate, a variable in the equations. Gödel solved those equations and found that they permit universes where time, in the sense that any human has ever understood the word, does not exist. The temporal ordering that we take for granted, the past, present, future sequence, the flow from cause to effect, is not required by the theory. Just as mathematical truth exceeds any formal system, physical reality exceeds our temporal intuitions. The equations contain more than their creator intended, and what they contain cannot be removed without destroying the theory. Rebecca Goldstein, in her 2005 book Incompleteness, argued that both results reflect Gödel's deep Platonism, his conviction that reality possesses features that transcend our formal descriptions and our intuitive expectations. Solomon Pfefferman cautioned against overextending the analogy. The incompleteness theorems and the rotating universe operate in different domains, using different methods with different logical structures. The parallel is more temperamental than technical. But at the level of intellectual method, the thread is unmistakable. The philosopher Hao Wang described Gödel's approach as the method of bold generalization, the practice of taking a system seriously, more seriously than its creators did, and following the consequences wherever they lead, even into territory that the system's designers would have preferred to avoid. That is what Gödel did to arithmetic. That is what Gödel did to space-time. And in both cases, the consequences were devastating. But here is what you were not told. The 1949 result was not a quirky thought experiment. It was not a curiosity. It was not a what-if scenario that physicists could file away under interesting but irrelevant. Gödel's proof used the same general relativity that predicts gravitational lensing, that tells GPS satellites how to correct for time dilation, that detected gravitational waves at LIGO in 2015 with a precision of 1 part in 10 to the 21st power. The equations are not speculative. They are the most precisely tested theory of gravity in the history of physics. And those equations, when Gödel solved them for a universe containing rotating matter balanced against a cosmological constant, produced a space-time in which you can get in a rocket ship, fly a sufficiently wide curve, and arrive back before you left. Not arrive at a place that looks like the past. Arrive at the actual, literal past. The same event, the same moment. Because in Gödel's universe, the distinction between past and future does not exist. Einstein read the proof. He checked the math. And in his written response, published in the same volume where Gödel's philosophical essay appeared, a Festschrift for his 70th birthday called Albert Einstein, Philosopher-Scientist, edited by Paul Arthur Schilp and produced in a signed limited edition of just 760 copies. He admitted that the result constituted, in his opinion, an important contribution to the general theory of relativity, especially to the analysis of the concept of time. He wrote that the problem Gödel identified had disturbed him since the very beginning, since he first built the general theory, and that he had never succeeded in clarifying it. His only hope, expressed carefully in that same response, was that Gödel's solution might somehow be excluded on physical grounds, meaning he could not find a mathematical error. He could not identify a logical flaw. The father of general relativity was left hoping his own theory would turn out to be more restrictive than it appeared. 3 years later, in 1952, Einstein went further. He told Oscar Morgenstern that Gödel's paper was one of the most important on relativity since his own original paper appeared. That is Einstein, speaking privately, ranking Gödel's 4-page paper alongside the foundational work of general relativity itself. And Stephen Hawking, decades later, confirmed the significance from the other direction. Gödel was the first to show that time travel was not forbidden by the Einstein equations, Hawking wrote. His solution generated a lot of discussion of the relation between general relativity and the concept of causality. Hawking added something else, something that reveals just how deeply the result cut. That his equations might allow this possibility really upset Einstein, who had thought that general relativity would not allow time travel. The word upset is doing a lot of work in that sentence. Einstein had spent a decade building general relativity. He had built time into the fabric of the universe, and his best friend had proved that the fabric does not require time to be real. It did not. And what happened next, the 75 years of silence that followed, is one of the strangest episodes in the history of science, because Gödel's proof did not just show that time travel is possible. That is the pop science headline, and it is almost trivially incomplete. What Gödel actually proved is that the concept of time, the flow you feel, the before and after, the sequence in which things happen, is not required by the laws of physics, and therefore it is not a fundamental feature of reality. It is optional. It is an accident of the particular universe you happen to live in. And accidents are not truths. That would be disturbing enough on its own. But Gödel's result was not the last time the equations of physics would produce a world without time. Something worse was coming. It would take another 18 years before anyone wrote it down. And when they did, it would not be a special solution or an exotic spacetime. It would be the most fundamental equation in quantum gravity, and it would contain no time variable at all. You were never told any of this, and the question you should be asking is why. If Gödel proved in 1949 that time is not real, and Einstein confirmed the proof was valid, and no physicist in the 75 years since has produced a mathematical refutation, then what exactly has the physics community been doing? That question does not have a simple answer. It has a complicated, uncomfortable, and increasingly damning one. But before you can understand the full weight of what Gödel discovered and why it was buried, you need to understand what his 4-page paper actually says. Not the pop science version, not the Wikipedia summary. The actual geometry of what happens to time when matter rotates. The paper's title was deliberately understated, as Gödel's titles always were. An example of a new type of cosmological solutions of Einstein's field equations of gravitation. A new type, as though he were presenting a minor variation on existing work. What he was presenting was the first exact solution to Einstein's equations in which time travel is permitted for every observer at every point in the universe. The solution describes a cosmos filled with pressureless dust, matter distributed uniformly throughout all of space, rotating rigidly. The rotation is balanced against a negative cosmological constant in a precise relationship. Lambda, the cosmological constant, equals -4 pi times the gravitational constant times the density of the dust, which also equals negative omega squared, where omega is the angular velocity of the matter. Every quantity is locked to every other quantity. The solution is not approximate. It is not a perturbation of some simpler model. It is exact. And the space-time it describes is, in every mathematical sense, well-behaved. It is homogeneous, meaning every point in the universe looks exactly the same as every other point. There is no center, no edge, no special location. It admits a 5-dimensional group of symmetries, which is actually more symmetry than the standard cosmological models possess. It has no singularities, no edges, no places where the math breaks down. It is geodesically complete, meaning a particle can travel through it forever without hitting a boundary. It is, technically speaking, a perfectly valid universe, one of the rare exact solutions that is entirely regular. No pathologies, no exotic matter, just dust, rotation, and a cosmological constant. The only thing wrong with it, the only feature that separates it from the textbook Friedman models you learn about in a cosmology class, is that it contains closed, time-like curves. You need to understand what that phrase means, because it is the hinge on which everything turns. In general relativity, space-time is not a stage on which events happen. It is a geometric structure. Every event, every point in space-time, has a light cone attached to it. The light cone represents the set of all possible futures of a particle at that event. The surface of the cone is traced by light rays. The interior of the cone, the time-light region, is where massive particles can travel. Anything with actual mass moving below the speed of light. A time-like curve is a path through space-time that stays inside these cones at every point along the way. It represents a physically realizable journey. You are tracing a time-like curve right now. Your world line, the path you follow through space-time from birth to death, is a time-like curve. It points forward. It always points forward. You move from past to future, from cause to effect, from birth to death. You never double back. A closed, time-like curve is a time-like path that loops. It returns to its starting point. An observer traveling along one would, from their own local perspective, always be moving forward through time, always aging normally, always perceiving cause before effect, and yet they would arrive back at the exact event from which they departed. They would meet their younger self. They would occupy the same point in space-time they left from. The curve is closed in the same way a circle is closed, not because you turned around, but because the geometry of the space curves back on itself. In Gödel's universe, these curves exist because the rotation of matter does something extraordinary to the geometry of space-time. It drags the light cones. Near any given point, close in, the tilting is modest. Light cones point roughly upward, in the time direction, the way you expect. Space is mostly space, time is mostly time. But as you move outward from any point in a specific direction, the cones begin to tip. The rotation of the matter around you twists them, progressively in the direction of the rotation. At a critical distance, defined mathematically by the condition that the hyperbolic sine squared of the radial coordinate equals 1, approximately at a radial distance of log of 1 plus the square root of 2, the tilting reaches a threshold. The angular direction, which was space-like near the center, meaning you could not travel along it without exceeding the speed of light, becomes timelike. It flips. And once a spatial direction becomes timelike, you can travel along it at less than light speed. You can travel in a circle in time just as easily as you can travel in a circle in space. The curves are not geodesics. You cannot drift along them passively the way a planet drifts along its orbit around a star. Traversing them requires sustained rocket acceleration, a minimum speed of approximately 70.7% of the speed of light, 1 over the square root of 2 times c. The journey would be enormous. The mathematician David Malamud calculated in 1984 and 85 that the radius of the curve you need to trace is cosmological in scale. You would not be looping around a building, or a city, or a solar system. You would be tracing a path through a significant fraction of the observable universe, burning fuel continuously at nearly 3/4 of light speed for what would be, by any practical measure, an absurdly long time. The energy requirements would dwarf anything humans have ever contemplated. This is sometimes cited as a reason not to worry. It should not be. That objection confuses the difficulty of building a bridge with the impossibility of crossing a river. The river is crossable. The geometry permits it. Whether you have a bridge is an engineering question, not a physics question. And physics is what Gödel was talking about. He was not proposing a time travel mission. He was making a statement about the structure of reality. The fact that time loops are permitted by the geometry of his space-time, even if they are difficult to traverse, means that the distinction between past and future is not absolute. It is a coordinate label, like north and south, that depends on the shape of the space you are in. In a flat space, north and south are distinct everywhere. On a sphere, you can keep walking north and end up heading south. In Gödel's space-time, you can keep moving forward in time and end up in the past. The geometry does not care about your fuel reserves. And because Gödel's space-time is homogeneous, the critical radius exists around every point. There is no safe zone. Closed timelike curves do not exist only in some exotic corner of the universe. They pass through every single event. There is no region, no neighborhood, no hiding place where time works the way you think it should. The entire universe is permeated by the possibility of returning to your own past. Gödel was fully aware of what this implied. He wrote it down explicitly. This state of affairs seems to imply an absurdity, he noted, for it enables one to travel into the near past of those places where he has himself lived. There he would find a person who would be himself at some earlier period of life. Now he could do something to this person which, by his memory, he knows has not happened to him. The grandfather paradox. Gödel did not try to resolve it. He wielded it. If the laws of physics permit situations that contradict the very notion of temporal order, then temporal order is not a law of physics. It is something else. And here is where Gödel did something that no other physicist who has ever found closed time-like curves in general relativity has done, before or since. He did not stop at the mathematics. He published a companion essay in the Einstein Festschrift titled A Remark About the Relationship Between Relativity Theory and Idealistic Philosophy, laying out a philosophical argument of devastating precision. It had 5 steps, and it still has not been answered. Step 1. Gödel defined what objective time requires. For the passage of time to be real, Reality must consist of an infinity of layers of now that come into existence one after another. The past must genuinely no longer exist. The future must genuinely not yet exist. The present must be the boundary between them. Step 2. Special relativity already threatens this picture. The relativity of simultaneity means that different observers, moving at different velocities, disagree about which events are happening at the same time. Each observer has their own set of now layers, and no observer's set is more correct than any others. There is no fact of the matter about what is happening right now on a distant star. It depends on how you are moving. Step 3. Standard cosmological models appeared to rescue objective time from this threat. In a Friedman universe, the kind that describes our actual expanding cosmos, matter is distributed uniformly and expanding uniformly. You can define a preferred set of observers, the co-moving observers who are at rest with respect to the average motion of the matter around them. Relative to these observers, you can define a cosmic time that all of them agree on. This looks like the objective time that special relativity threatened. Step 4. Gödel's rotating universe destroys the rescue. In his solution, there is no way to define a consistent global time. For any proposed definition of world time, any attempt to slice the universe into layers of simultaneous events, there exist paths that carry you into regions that are in the past, according to that very definition. Every proposed now can be violated. Every attempt to impose temporal order on the universe fails. The concept of a universal present marching steadily forward cannot be constructed. Step 5. The kill shot. Even though our universe may not rotate, even though cosmic time can be defined in our particular cosmos, the mere physical possibility of Gödel's universe is enough to destroy objective time everywhere, because his universe and ours are governed by the same laws, the same field equations, the same general relativity. If those laws permit a universe where objective time does not exist, then objective time is not a consequence of the laws. It is a feature of initial conditions, of the specific arrangement of matter in our universe. And features of initial conditions are not fundamental truths. They are accidents. Think of it this way. The experience of time passing is compatible with the absence of objective time. Gödel's universe proves this by construction. An observer inside his rotating cosmos would experience time passing in exactly the same way you experience it right now. They would feel the seconds tick forward. They would remember the past and anticipate the future. They would perceive cause and effect. And yet, in their universe, time does not objectively pass. There is no global now. There is no objective ordering of events. The feeling is identical, but the reality is absent. If the feeling of time passing can exist without time actually passing, then the feeling proves nothing about whether time actually passes in our universe. You cannot use the experience as evidence. The experience is compatible with both possibilities. This is not a hand-waving philosophical argument. It is a logically rigorous application of modal reasoning to the structure of general relativity. Gödel was not speculating, he was proving. His conclusion was stated with the bluntness of a logician who has spent his career stating unwelcome truths. Change is an illusion or an appearance due to our special mode of perception. He strengthened this position in an addendum dated September 2nd, 1949. In the interim, he wrote, "I have discovered that there are solutions for any values of the cosmological constant for which no universal time exists. This was not a minor refinement. It removed the objection that his result depended on a precisely tuned cosmological constant. The death of time was not an artifact of a special parameter. It was woven into the theory itself. It lived in the equations no matter what value you assign to lambda. Now, you might think you already knew that Gödel showed time travel is possible. That is the version that survives in popular accounts and 15-minute YouTube videos. But what Gödel actually showed is far more disturbing than time travel. Time travel is the mechanism. The death of time is the conclusion. And the difference matters enormously, because time travel can be dismissed as engineering. You can wave it away by saying the energy requirements are absurd, or our universe does not rotate, or some future law of physics will prevent it. But the death of time cannot be dismissed that way. Gödel's argument is not about what is practical. It is about what the laws of physics reveal about the structure of reality. And what they reveal is that reality does not require time to pass, that the flow you feel is not encoded in the equations, that it is something your brain does, not something the universe does. Einstein knew this. He could not escape it, and neither could the physics community, but they found something almost as good as an escape. They found a way to stop talking about it. But the silence was not just about Gödel's equations. It was about Gödel himself. Because the man who proved time is an illusion was not some fringe figure working alone in a basement. He was the closest intellectual companion Albert Einstein had in the last decade of his life. And the story of their friendship reveals something important about what the physics community was actually avoiding and why the avoidance lasted so long. Kurt Friedrich Gödel was born on April 28, 1906, in Brunn, Austria-Hungary, a city now called Brno in the Czech Republic. His father Rudolf was the managing director of a textile firm. His mother Marianne was well educated, having studied partly in France. The family was prosperous. They had servants and a governess. Kurt had an older brother, also named Rudolf, born in 1902, who would become a radiologist. The family nickname for the younger boy was Der Herr Warum, Mr. Why, because he asked questions incessantly from the moment he could talk about everything. At age 6, he suffered rheumatic fever. He recovered completely. But at age 8, he found a medical textbook and read about the disease. He became convinced his heart had been permanently damaged. The belief was false, but he carried it for the rest of his life. This was the first sign. The hypochondria, the fixation on illness, the conviction that his body was failing despite all evidence to the contrary, would deepen over decades until it consumed him. At the Deutsches Staatsrealgymnasium in Brunn, he excelled in every subject. He never received a grade below the highest mark. He never made a single error in Latin grammar in his entire school career. By the time he was 16, he was reading Kant and working on university-level mathematics. He enrolled at the University of Vienna in 1924, initially intending to study theoretical physics, but lectures on number theory by Philipp Furtwängler, a professor who was paralyzed from the neck down and lectured from a wheelchair while an assistant wrote on the board, turned him toward mathematics. He found his way to Hans Hahn's seminars and to the Vienna Circle, the famous group of positivist philosophers who met regularly to discuss the foundations of science, language, and meaning. Moritz Schlick led the group. Rudolf Carnap was a central figure. Otto Neurath, Friedrich Waismann, and Herbert Feigl were regulars. Gödel attended their meetings faithfully throughout the late 1920s. He listened. He rarely spoke. And he privately disagreed with almost everything they believed. The Vienna Circle championed logical positivism, the doctrine that only statements verifiable through sense experience or logical analysis have meaning. Metaphysical claims, ethical claims, aesthetic claims, anything that could not be empirically tested or logically derived, they declared meaningless. This was the dominant philosophy of science in the early 20th century. Gödel rejected it utterly. He was a Platonist to the core, convinced that mathematical objects exist independently of human minds. That truth is discovered, not invented, that reality has objective features that outstrip our ability to formally capture them. He kept these views largely to himself. During the Vienna years, it would take his incompleteness theorems to begin making the case, and decades more before the full implications of his Platonism became clear. His fellow student Olga Taussky-Todd recalled that it slowly became obvious that Gödel would stick with logic, that he was to be Hahn's student and not Schlick's, and that he was incredibly talented. The incompleteness theorems made him famous in 1931, but the fame was of a peculiar kind. Among mathematicians and logicians, he was recognized immediately as a figure of the first magnitude. Among the broader public, he was unknown, and among many working mathematicians, his result was received with something between confusion and resentment. It said, in effect, that mathematics has permanent limits, that there will always be true statements you cannot prove, that no amount of cleverness or effort will make mathematics self-contained. This is not a message that mathematicians enjoy hearing. He first visited the Institute for Advanced Study in Princeton in 1933. He returned in 1935 and again in 1938. During the 1930s, his mental health deteriorated. In June 1936, Moritz Schlick, the founder of the Vienna Circle and one of Gödel's teachers, was shot and killed on the steps of the University of Vienna by a former student named Johann Nelberg. The murder was motivated by a combination of personal grudge and anti-Semitic, pro-Nazi sentiment, though Schlick himself was not Jewish. Nelberg received a light sentence and was celebrated by some as a hero. The incident shattered Gödel. He called 1936 one of the 3 worst years of his life. He spent time in sanatoria. His weight dropped to 48 kilograms. He became convinced people were trying to poison him. Receipts from this period show him trying to purchase a handbook on toxicology. In September 1938, he married Adele Nimbursky, born Porkert. They had met in 1927 at a Viennese nightclub called Der Nachtfalter, the Moth. She was a trained ballet dancer, 6 years older than him, previously divorced, Catholic. His parents disapproved of her on grounds of class, age, and religion. The courtship lasted 11 years. Adele was not an intellectual. She had no university education. She was warm, practical, earthy, and entirely undaunted by Gödel's genius or his illness. She became his lifeline in a way that no theorem or proof could match. She addressed him as Strammer Bursche, strapping lad. George Kreisel, a logician who knew them both, said it was a revelation to see Gödel relax in her company. She had a less charitable nickname for the Institute for Advanced Study. She called it the Altersversorgungsheim, the home for old age pensioners. On March 4, 1940, Kurt and Adele arrived permanently in the United States. They had escaped Nazi-occupied Austria through an extraordinary route, one that reads like something out of a spy novel. After the Anschluss in March 1938, Austria was absorbed into the Third Reich. Gödel's academic position evaporated. The title of Privatdozent, which had granted him the right to lecture at the University of Vienna, was abolished by the new regime. He applied for a new position under the restructured system and was rejected. More dangerously, he was classified as fit for military service by the Nazi authorities, despite his frail health and history of nervous breakdowns. The prospect of being drafted into the Wehrmacht was very real. The couple could not go west. The Atlantic was patrolled by German U-boats, and the ports of occupied Europe were under surveillance, so they went east. In January 1940, they boarded a train from Vienna, traveled across the vast frozen expanse of the Soviet Union on the Trans-Siberian Railway, a journey of approximately 6,000 miles and several days, to Vladivostok on the Pacific coast. From Vladivostok, they took a ship to Kobe, Japan, then another ship across the Pacific to San Francisco. From San Francisco, they crossed America by train to Princeton. The entire journey covered roughly 15,000 miles and took several weeks. It was the farthest Gödel would ever travel from Princeton. He never left the United States again. He would spend the remaining 38 years of his life within a few miles of the Institute for Advanced Study, increasingly within a few rooms of his house on Linden Lane, and eventually within the confines of Princeton Hospital. At Princeton, he became a permanent member of the Institute for Advanced Study in 1946 and a full professor in 1953. The delay is telling. Despite being recognized as one of the greatest logicians in history, despite Einstein's advocacy, the Institute was slow to grant him full status. Part of this was institutional caution. Part of it may have been that Gödel's genius was of a type that made administrators nervous. He proved things people did not want to hear, and it was during the 1940s, in the quiet of Princeton, surrounded by exiles and intellectuals, and the peculiar greenhouse atmosphere of the Institute, that the friendship with Einstein deepened into something unprecedented. From the mid-40s until Einstein's death, they walked together nearly every day. The image became famous at the Institute. Einstein, rumpled, sockless, in his leather jacket, his white hair uncombed. Gödel beside him, trim, precise, in a white linen suit and matching fedora even in the heat of New Jersey summers. They spoke German. They talked about physics, philosophy, the nature of time, the foundations of mathematics, the failures of quantum mechanics. Einstein was by this point deeply isolated in his own way. His quest for a unified field theory was going nowhere, and most of his younger colleagues had written him off. He rejected quantum mechanics and its probabilistic core, putting him at odds with nearly the entire physics community. Gödel rejected the positivist philosophy that dominated mid-century thought, putting him equally at odds with the prevailing intellectual winds. They were both contrarians, they were both realists, and they were both, in different ways, right about things that the mainstream had dismissed. Einstein confided to Morgenstern that his own work no longer meant much, that he came to the Institute merely to have the privilege of walking home with Kurt Gödel. Freeman Dyson observed that Gödel was the only one of their colleagues who walked and talked on equal terms with Einstein. Another Institute member recalled that they did not want to speak to anybody else. They only wanted to speak to each other. What did they talk about? Physics, certainly. Philosophy, certainly. The nature of time, which Einstein had thought about since 1905. and which Gödel was beginning to think about with the tools of mathematical logic. They discussed quantum mechanics, which Einstein rejected on philosophical grounds, and which Gödel found dissatisfying for similar reasons. Both men were realists. Both believed the physical world has an objective existence independent of observation, a position that put them fundamentally at odds with the Copenhagen interpretation that dominated mid-century physics. Bohr's philosophy, which held that quantum mechanics does not describe reality but only our knowledge of reality, struck both Einstein and Gödel as a kind of intellectual surrender. They agreed on this profoundly, and it bound them together in an era when most of their colleagues had accepted Copenhagen and moved on. They also discussed the nature of mathematics. Gödel was a Platonist. He believed that mathematical objects, numbers, sets, structures, exist independently of human minds. They are discovered, not invented. Mathematical truth is objective in the same way that physical truth is objective. The number 7 existed before humans and will exist after them. This was deeply unfashionable in an era dominated by logical positivism and formalism. Philosophies that treated mathematics as a human construction, a game played with symbols according to arbitrary rules. Gödel's incompleteness theorems had, in a sense, vindicated his Platonism by showing that mathematical truth outstrips any formal system humans can construct. There are truths that are true and cannot be proven, which implies that truth is out there, independent of the proving. Einstein seems to have found in Gödel not just an intellectual equal, but a philosophical ally. They were both fighting the same battle on different fronts. Einstein against the positivist interpretation of quantum mechanics. Gödel against the positivist interpretation of mathematics. And both of them increasingly against the positivist tendency to dismiss questions about reality as meaningless whenever the questions became too uncomfortable. It was in this context, intellectual and personal, that Gödel turned his attention to general relativity. He taught himself the mathematics. He studied the known solutions, and then he found a new one. His rotating universe, presented in the Festschrift for Einstein's 70th birthday on March 14, 1949, was not just a mathematical result. It was a conversation between friends that happened to destroy one of the most basic features of human experience, a birthday gift that killed time. Think about what that means for the institutional response. It was not just any physicist presenting a troubling result. It was Einstein's closest friend, using Einstein's own equations in a volume celebrating Einstein's birthday, with Einstein's explicit written acknowledgement that the result was important and that he could not refute it. The physics community was not just ignoring a paper. They were ignoring the most prestigious endorsement imaginable from the most famous scientist in history of a result produced by the man that scientists considered his only intellectual equal. There is a story about Gödel that captures the essential nature of the man, the way his logical mind operated on everything it encountered, including things that were never meant to be subjected to rigorous analysis. In 1947, Gödel applied for American citizenship. Einstein and Morgenstern agreed to serve as his witnesses at the hearing. In preparation, Gödel studied the United States Constitution with the same intensity he brought to Hilbert's axioms. And he found something. He told Morgenstern that he had discovered a logical inconsistency in the Constitution that would permit the United States to be legally transformed into a dictatorship. Morgenstern and Einstein were alarmed. They begged him not to bring it up during the hearing. They coached him on the drive to Trenton when the judge asked Gödel where he came from. Gödel said, Austria. The judge said that was a terrible dictatorship. Gödel agreed, and then added that it could happen here too, because he had found a flaw in the constitution that would allow it. The judge, to his eternal credit, said something like, "Oh God, let us not go into this." He was granted citizenship. Einstein and Morgenstern had spent the car ride sweating. But that was Gödel. He could not encounter a formal system without looking for what it contained that its creators had not intended. The Constitution, Hilbert's axioms, Einstein's field equations. He found the hidden truth in all of them. And in all of them, the hidden truth was uncomfortable. The dismissal of his cosmological work took a specific form. Gödel's universe does not rotate. Our universe, based on the near-perfect isotropy of the cosmic microwave background radiation, does not appear to rotate. Current observational bounds constrain any cosmic rotation to less than 10 to the negative 17th degrees per century. That is less than one revolution in 100 billion trillion years, effectively zero. Therefore, the argument went, Gödel's solution does not describe our universe. Therefore, it can be set aside. Gödel's counter-argument, his step 5, his transfer argument, was simply never engaged with. If the laws permit a universe without time, then time is not a consequence of the laws. This is a logical point, not an empirical one. It cannot be dismissed by measuring the rotation of the cosmic microwave background. It requires a philosophical response, and no philosophical response was ever provided. The physics community treated it as though measuring the rotation rate was sufficient. It was not. It never was. Hawking, decades later, recorded a detail that captures the situation with painful clarity. Throughout his final years, Gödel would ask every visiting cosmologist the same question: is the universe rotating yet? And each time, the answer was no, it is not. They thought he was asking about observation. He was asking whether anyone had grappled with the argument. Nobody had. And while the physics community was busy not grappling with Gödel's argument, while they were filing his rotating universe under mathematical curiosities and moving on, two things happened that should have forced a reckoning, but did not. The first was Gödel's own follow-up. In 1950, and again at the International Congress of Mathematicians in 1952, Gödel presented new cosmological solutions that combined rotation with expansion. These models were closer to the real universe. They had a Hubble flow. They were expanding. And while these particular expanding and rotating models did not contain closed, time-like curves, they demonstrated something important. Gödel's original result was not an isolated accident. It was part of a landscape of solutions in which rotation and time interacted in unexpected ways. The connection between rotation and the failure of global time was not a fluke of one specific metric. It was a general feature of how matter and geometry relate in Einstein's theory. Hawking himself acknowledged that Gödel's expanding, rotating solutions could well be a reasonable description of the universe that we observe, with the caveat that observational data constrain the rotation rate to be very low. But very low and zero are different claims, and the philosophical argument does not depend on the rotation rate being large. It depends on the rotation rate being physically possible, which it is. The second thing that happened was that closed, time-like curves showed up somewhere else entirely, in a completely different solution, under completely different physical conditions, and they kept showing up, over and over, in solution after solution. as though the equations of general relativity were trying to tell physicists something they did not want to hear. The first reappearance was inside a black hole. In 1963, the New Zealand mathematician Roy Kerr found the exact solution to Einstein's equations, describing a rotating black hole. The Kerr metric became one of the most important results in 20th century physics. It describes every astrophysical black hole with angular momentum, which, as far as we can determine, is every black hole in the actual universe. Stellar mass black holes formed from collapsing stars rotate because the stars that formed them were rotating. Supermassive black holes at the centers of galaxies rotate because the accretion disks that feed them carry angular momentum. The two black holes whose merger was detected by LIGO on September 14, 2015, the event that opened the era of gravitational wave astronomy, were both rotating. The Kerr metric is not a mathematical toy. It is not an exotic hypothetical. It describes objects we have detected, measured, and photographed. And deep inside the Kerr solution, beyond the outer event horizon, beyond the inner Cauchy horizon, in a region that a falling observer would traverse in finite proper time, the metric contains closed, time-like curves, time loops, inside the most common type of astrophysical object in the cosmos. Physicists point out correctly that the inner Cauchy horizon of a Kerr black hole is almost certainly unstable. Work by Penrose, Simpson, and others in the late 1960s and early 70s showed that any realistic perturbation, any infalling radiation or matter would cause the Cauchy horizon to become singular, collapsing into an impassable barrier before any observer could reach the CTC region. This is the mass inflation instability, and it is probably fatal to any hope of using a Kerr black hole as a time machine. But notice again what the response amounts to. The equations produce time loops. The response is to find reasons why you cannot reach them, not to ask why the equations produce them in the first place. The pattern was set by the reaction to Gödel, and it has never changed. The theory keeps generating temporal paradoxes. The physics community keeps finding engineering reasons to ignore them. In 1974, Frank Tipler showed that an infinitely long, rapidly rotating cylinder of extremely dense matter would produce closed time-like curves through frame dragging, the effect where massive rotating objects pull space-time around them. The cylinder must be infinitely long, which rules out practical construction. But Tipler noted that the infinite length requirement might be an idealization, and that a sufficiently long, sufficiently massive, sufficiently rapid cylinder might produce the same effects. Nobody proved him wrong. They just noted the impracticality and moved on. Then, in 1985, the problem crashed back into mainstream physics through an entirely unexpected door. Carl Sagan was writing his novel, Contact, the story of humanity's first communication with an extraterrestrial civilization, and he needed a scientifically respectable way to move his protagonist across interstellar distances quickly. Science fiction typically invokes hyperspace or warp drives, but Sagan wanted something grounded in real physics. He called Kip Thorne at Caltech, one of the world's foremost experts on general relativity, and the man who would later share the 2017 Nobel Prize for the detection of gravitational waves. Thorne thought about it and realized that traversable wormholes, hypothetical tunnels through the fabric of space-time connecting two distant regions, could serve as the transport mechanism. A wormhole is essentially a shortcut. The two mouths could be light years apart in ordinary space, but connected through the wormhole by a distance of mere meters. Thorne worked out the physics with his graduate students Michael Morris and Olvi Yurtsever and published 2 landmark papers in 1988, one in the American Journal of Physics, aimed at a general audience, and one in Physical Review Letters, aimed at the research community. The papers showed that traversable wormholes are consistent with general relativity, though they require exotic matter with negative energy density, to hold the wormhole throat open. Without the exotic matter, the wormhole collapses too quickly for anything to pass through. This is not as outlandish as it sounds. Quantum field theory permits negative energy densities in certain specific configurations. The Casimir effect, the measurable attraction between 2 closely spaced metal plates in a vacuum, is driven by negative vacuum energy between the plates. It was measured experimentally by Steve Lamoureux at the University of Washington in 1997. Whether nature permits enough negative energy to hold a macroscopic wormhole open is an entirely different and unanswered question. The time machine part came as an unwelcome surprise. If you take one mouth of a traversable wormhole and accelerate it to a high fraction of the speed of light, then bring it back, special relativistic time dilation means the 2 mouths are now at different times. The traveling mouth has experienced less time than the stationary mouth. Step through the stationary mouth, and you emerge from the traveling mouth in what the stationary mouth would call the past. You have built a time machine using only general relativity, special relativity, and a wormhole. No rotating universe required. No infinite cylinder, just a tunnel through spacetime and a fast rocket. The catch is exotic matter. Whether nature permits macroscopic amounts of negative energy matter is an open question. Quantum field theory permits negative energy densities in certain configurations, the Casimir effect being the most famous example. But whether you can accumulate enough to hold a wormhole open is unknown. Hawking himself proved that building a finite time machine requires negative energy density somewhere. He could not prove that nature forbids it. J. Richard Gott III at Princeton showed in 1991 that cosmic strings, one-dimensional topological defects, hypothetically produced during phase transitions in the early universe, could also generate closed Timelike curves if 2 strings pass each other at sufficient velocity. Cosmic strings have not been observed, and their existence remains uncertain. But their properties are predicted by standard quantum field theory applied to cosmological conditions. If they exist, general relativity says they can create time loops. Again, speculative in the observational sense, but the math is clean. The equations are general relativity unmodified. No new physics required. No exotic additions. Just the same theory that predicts the precession of Mercury's orbit and the deflection of starlight around the Sun, applied to a hypothetical but physically reasonable object producing a structure that allows travel to the past. By the early 90s, the situation had become, from a certain perspective, absurd. Physicists kept finding new ways to extract time machines from Einstein's equations: rotating universes, rotating black holes, traversable wormholes, cosmic strings, infinite cylinders, rotating dust shells, Misner space, Alcubierre drives. It was as though the theory was littered with temporal anomalies, and every time you closed one door, 2 more opened. The equations did not merely permit closed time-like curves in some narrow, exotic corner of the parameter space. They seemed to welcome them, to produce them naturally under a surprisingly wide range of physical conditions, with different matter content different symmetries, different topologies. Stephen Hawking decided to address this directly. On September 23, 1991, he submitted a paper to Physical Review D. It was published on July 15, 1992, Volume 46, Issue 2, pages 603 through 611. The title was Chronology Protection Conjecture. The key word is the last one. Conjecture. Not theorem, not law. Conjecture. A hypothesis, an educated guess. Hawking's argument was that quantum effects would prevent closed time-like curves from forming. Specifically, he argued that near any chronology horizon, the boundary in spacetime where CTCs first appear, the quantum vacuum energy would diverge. It would blow up. The back reaction of this energy on spacetime would prevent the horizon from forming, and therefore prevent the CTCs from appearing. The universe, he proposed, protects chronology. His famous concluding line was deliberately whimsical. It seems that there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians. As strong empirical evidence, he offered the fact that we have not been invaded by hordes of tourists from the future. The physics community received this with relief. Finally, someone had addressed the problem. The chronology protection conjecture entered textbooks, review articles, popular science books. It was cited thousands of times. It became the standard answer to the time travel question. Can general relativity produce time machines? Yes, but Hawking showed that quantum effects prevent them from actually forming. Problem solved. Except the problem was not solved. Hawking did not prove the conjecture. He supported it with calculations in specific spacetimes and offered heuristic arguments for why it should be true in general. But the specific calculations had gaps, and the heuristic arguments had exceptions. In the years following his paper, Matt Visser at Victoria University of Wellington and others found spacetimes where the vacuum energy does not diverge at the chronology horizon, or where the divergence is too weak to prevent CTC formation. Amos Ori at the Technion in Israel constructed a particularly troubling example. In 2005, Ori published in Physical Review Letters an exact vacuum solution to Einstein's equations, a spacetime containing no matter at all, just the pure geometry of empty space that develops closed time-like curves from perfectly regular initial conditions. No exotic matter, no rotating dust, no cosmological constant. Just vacuum, just geometry, and the geometry produces time loops. The chronology protection conjecture, at a minimum, does not apply in its simple form to Ori's solution. At a maximum, it suggests that the entire conjecture may be wrong. What the conjecture actually tells you, stripped of the humor and the reassurance, is damning. It tells you that Hawking considered the problem of closed time-like curves serious enough to require a new law of physics to address, not an application of existing physics. A new principle. He needed the universe to actively forbid something that its own equations explicitly permit, and he could not prove that it does. 33 years later, the conjecture remains unproven. A complete proof would require a theory of quantum gravity, which does not exist. The conjecture is widely believed among physicists, but believing and proving are different activities, and the physics community has often confused one for the other when the alternative is too uncomfortable to contemplate. And the discomfort was about to get much worse, because while Hawking was trying to protect chronology, quantum physicists were discovering that closed time-like curves are not just a problem for general relativity, They are woven into the fabric of quantum mechanics itself. David Deutsch at Oxford published a landmark paper in 1991. The same year, Hawking submitted his conjecture, titled Quantum Mechanics Near Closed Timelike Lines. Deutsch was not trying to build a time machine. He was asking a theoretical question about what quantum mechanics would look like in the presence of CTCs. His answer transformed the debate. In classical physics, the grandfather paradox produces logical contradictions. You go back and prevent your own birth, which means you were never born to go back, and so on. The paradox seems to forbid time travel by reductio ad absurdum. Deutsch showed that quantum mechanics dissolves the paradox entirely. In the many worlds interpretation, which Deutsch champions, a time traveler who enters a CTC emerges into a different branch of the multiverse. The grandfather in the original branch is unaffected. The time traveler interacts with a different version of the past. Self-consistent solutions always exist. The paradox was never a paradox at all. It was an artifact of classical thinking. This should not be comforting. Deutsch also proved that quantum computers with access to CTCs would be able to solve problems in the computational complexity class PSA-PSE. Scott Aronson and John Watrous formalized this in 2009. PSA-PSE contains problems that are believed to be intractable for any computer, quantum or classical, that we could ever build without time loops. The mere theoretical existence of CTCs would not just allow time travel, it would restructure the foundations of what is computable. Problems that would take longer than the age of the universe to solve on the best supercomputer ever built would become solvable in reasonable time if you had access to a closed, time-like curve. The implications for cryptography, optimization, artificial intelligence, and every other field that depends on computational complexity would be total. And the only thing preventing this is the unproven hope that nature does not permit CTCs to exist. Meanwhile, Igor Novikov and Kip Thorne took yet another approach. Instead of trying to prevent time travel, they asked what the rules would be if it happened. The Novikov self-consistency principle, formalized with Thorne and several colleagues in Physical Review D in 1990, states that the only events that can occur near a closed time-like curve are those that are globally self-consistent. You can travel to the past, but you cannot change it. Any event you participate in was always part of the history. The grandfather paradox does not arise because you cannot kill your grandfather, not because some mysterious force stops you, but because the laws of physics properly applied only permit self-consistent histories. Billiard ball experiments confirm this. If you set up a billiard ball to enter a time machine and knock its earlier self off course before it enters the machine, there always exists a self-consistent solution, where the ball glances off itself at just the right angle to redirect itself into the machine. Often, there are multiple solutions. The paradox dissolves not because time travel is impossible, but because the universe insists on consistency. This sounds like a clever resolution. It is not. It is, if you think about it carefully, something far more disturbing. It means the universe has preferences. It means that among all the possible things that could happen, reality selects only those histories that are globally consistent. Your free will in the vicinity of a time machine would be constrained not by physical barriers, but by the requirement that the universe makes sense as a whole. You could no more kill your grandfather than you could walk through a wall. not because of a force, but because of geometry. Because the shape of space-time near a CTC only admits certain trajectories, and trajectories that produce paradoxes are simply not among them. Seth Lloyd at MIT proposed an alternative framework in 2011, published in Physical Review Letters. Where Deutsch used many worlds, Lloyd used quantum teleportation, with post-selection aligning with Novikov's self-consistency principle. In Lloyd's model, paradoxical outcomes have zero probability. Nature conspires to prevent them. Some quantum fluctuation always intervenes. As Lloyd put it, some little quantum fluctuation would always whisk the bullet away at the last moment. You pull the trigger at your grandfather and the gun jams, or a bird flies into the bullet's path, or a quantum tunneling event causes the firing pin to miss the primer. Not because these events are likely in isolation, but because they are the only events compatible with the consistency of the closed, Timelike curve. Lloyd's group performed the first laboratory demonstration, sending a photon a tiny fraction of a second backward in time to interact with its earlier self. The result matched the theoretical predictions exactly. In 2002, a team from MIT, Caltech, Harvard, and Fermilab used Google's Sycamore quantum processor to create what they described as a holographic wormhole simulation, published in Nature. And in October 2003, Cambridge researchers published in Physical Review Letters a demonstration that simulating closed, time-like curves produces measurable advantages in quantum metrology, advantages that are impossible under standard physics. The lead author stated that they were not proposing a time travel machine, but they had shown that the mathematical structure of CTCs has real, detectable physical consequences. Every escape route has been tried. The observational dismissal, the chronology protection conjecture, the appeal to quantum paradoxes. None of them has worked. The observational dismissal was anticipated and countered by Gödel himself in 1949. The conjecture remains unproven 33 years after it was proposed. The quantum approaches have embedded CTCs deeper into the structure of physics, not removed them. The equations keep producing time loops under classical and quantum conditions alike, and the physics community keeps finding new reasons to look the other way. In 2017, Daniel Jafferis and Ping Gao at Harvard, with Aaron Wall, found something that should have attracted far more attention than it did. They constructed the first traversable wormhole solution in general relativity that requires no exotic matter at all. None. Instead of negative energy, their wormhole is held open by quantum entanglement between the two mouths of the wormhole. The solution exploits a deep and still mysterious connection between quantum entanglement and the geometry of spacetime, known as the ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013. ER refers to Einstein-Rosen bridges, the mathematical name for wormholes. EPR refers to Einstein-Podolsky-Rosen entanglement, the quantum correlation between distant particles. The conjecture says these are the same thing, that every pair of entangled particles is connected by a microscopic wormhole, that the fabric of spacetime is literally sewn together by quantum entanglement. If this is correct, and a growing body of theoretical evidence suggests it might be, then wormholes are not exotic, they are everywhere. They are what spacetime is made of. The Gao-Jafferis-Wall wormhole is not a time machine by itself, but it removed the last clean objection to traversable wormholes, the need for exotic matter. And traversable wormholes, as Thorne showed in 1988, can be converted into time machines. The chain of logic that runs from Gödel through Kerr, through Thorne, through Gauss-Jaffer's-Wall, is unbroken. At every link, the equations of physics permit or actively facilitate structures that undermine the absolute distinction between past and future. And then there is the confirmation that nobody talks about, the one that does not involve time machines at all, the one that says, in the most fundamental equation physics has produced about the universe as a whole, that time simply is not there. In 1965, John Archibald Wheeler had a layover at the Raleigh-Durham Airport in North Carolina. Wheeler was one of the giants of 20th century physics. He had worked on the Manhattan Project, coined the term black hole, and spent decades thinking about the deep structure of spacetime. He was traveling somewhere else that day. He had about 2 hours to kill. So he called Wheeler-DeWitt at the University of North Carolina and asked if they could meet. DeWitt drove to the airport. He brought with him the Hamilton-Jacobi formulation of general relativity, the classical equation governing the dynamics of the gravitational field, written in a form that was ripe for quantization. And he suggested to Wheeler that they try to do for gravity what Schrödinger had done for the hydrogen atom in 1926. Take the classical equation, promote the variables to quantum operators, and see what the quantum theory of the universe looks like. This was not a new idea. Others had attempted it, but the formulation DeWitt presented was clean and direct, and Wheeler was a man who could recognize the significance of an equation the way a musician can recognize the significance of a chord progression. He was, by all accounts, tremendously excited. He declared on the spot that the equation for quantum gravity had been found. The declaration was premature in one sense, because quantum gravity remains unsolved more than 60 years later, and the Wheeler-DeWitt equation is at best an approximation to whatever the final theory turns out to be. But in another sense, Wheeler was exactly right. The equation captures something that any quantum theory of gravity must reckon with, a feature so deep and so disturbing that it has resisted every attempt at elimination. DeWitt published a full version in 1967. It became known as the Wheeler-DeWitt equation. And what it says about time is the single most important thing that quantum gravity has told us about the nature of reality. The ordinary Schrödinger equation, the one every physics student learns, has the form, the Hamiltonian operator acting on the wave function, equals I times h bar times the partial derivative of the wave function with respect to time. Time appears explicitly. It sits on the right side of the equation, governing how the quantum state evolves from one moment to the next. The wave function changes. Things happen. Time passes. The Wheeler-DeWitt equation has a different form. The Hamiltonian constraint acting on the wave function of the universe equals 0. 0. The right side is not I times h bar times a time derivative. It is 0. There is no time derivative. There is no time variable. The wave function of the entire universe, the quantum state that encodes everything that exists, does not evolve. It does not change from one moment to the next, because there are no moments. There is no next. The universe, at the most fundamental level the Wheeler-DeWitt equation can describe, simply exists. Static, timeless, complete. This is not an oversight. It is not a mathematical artifact that some cleverer formulation will fix. It is a direct, inescapable consequence of one of the deepest principles in general relativity, the principle of general covariance. General covariance says that the laws of physics must be valid regardless of what coordinate system you use to describe space-time. Any labeling of events, any choice of time coordinate, is as good as any other. None is preferred. When you quantize a theory with this symmetry, when you apply the rules of quantum mechanics to the gravitational field, this coordinate freedom becomes a constraint. The Hamiltonian, which in ordinary quantum mechanics generates time evolution, is forced to equal zero. It does not generate anything. It constrains. The result is called the problem of time in quantum gravity. It has been called by physicists working on quantum gravity the deepest problem in all of theoretical physics. It is not a puzzle waiting for a solution. It is a foundational crisis, the most fundamental description of the universe that physics can currently produce does not contain time, and physicists have been debating what this means and whether it can be resolved for nearly 60 years. Various attempts have been made to put time back in. Some physicists argue that time must be introduced as an additional ingredient, that the Wheeler-DeWitt equation is incomplete, that a fuller theory of quantum gravity will restore time to its rightful place. Others argue that time should be identified with some internal variable of the system, that a particular configuration of matter or geometry can serve as a clock, and that the wave function evolves with respect to this internal clock, even though it does not evolve with respect to an external time parameter. This approach works in some special cases, but breaks down in general. The choice of internal clock is not unique. Different choices give different physical predictions. And in the deep quantum gravity regime near the Planck scale, all candidate clocks fluctuate wildly. There is no stable reference to play the role of time. Still others, and this is the view that has gained the most traction in recent decades, argue that time is genuinely absent from the fundamental theory, and that the appearance of time is something that must be derived, not assumed. This is the view associated with Rovelli, with Barbour, and with a growing number of physicists who take the Wheeler-DeWitt equation at face value. The universe, at the deepest level, does not change. What we call change is an approximation. What we call time is a derived quantity. What we call the flow from past to future is a macroscopic illusion that emerges from the timeless quantum state, in the same way that temperature emerges from the random motion of molecules. Carlo Rovelli, one of the founders of loop quantum gravity, said it directly. I got interested in the nature of time because of quantum gravity. It is well known that the basic equations of quantum gravity can be written without a time variable. And I wanted to fully understand what this means. What it means in Rovelli's framework is that time is not a river carrying us forward. It is a lens through which we view a reality that has no forward. Think about what this means in the context of everything we have discussed. In 1949, Gödel used classical general relativity to show that the laws of physics permit universes without objective time. His conclusion was that time is not fundamental. In 1967, Wheeler and DeWitt quantized the same theory and found that the resulting equation, the equation that describes the universe as a whole, has no time in it at all. Gödel arrived at the conclusion through a specific, elegant solution. Wheeler and DeWitt arrived at it through the general structure of the quantized theory. Two completely independent routes, two unrelated methods, the same destination. Time is not fundamental. And then came the third route. In 1993, Carlo Rovelli and Alain Connes proposed the thermal time hypothesis. If time is not fundamental, they asked, then why do we experience it? Why does it feel like things happen? Why do you remember the past and not the future? Why does the second hand on a clock move forward and not backward? Their answer was radical, elegant, and deeply unsettling. Time, they proposed, is not written into the laws of the universe. It emerges from thermodynamics. Specifically, it emerges from our ignorance. Here is the logic. The universe, at the microscopic level, may be described by a timeless quantum state, exactly as the Wheeler-DeWitt equation suggests. But we do not have access to the microscopic level. We see the macroscopic world. We see averages and approximations and coarse-grained descriptions. And when you take a timeless quantum system and describe it using the tools of statistical mechanics, when you coarse-grain it, something remarkable happens. A flow appears. A parameter emerges that behaves exactly like time. Not because time is real, but because your partial view of an underlying timeless reality creates the appearance of change. Rovelli developed this into a full framework over the following decades. His 2018 book, The Order of Time, dismantled the common understanding of time, feature by feature. Start with the unity of time. You think there is one time, one clock, ticking at the same rate everywhere. There is not. Clocks tick at different rates depending on gravitational field strength. A clock on the floor of your room ticks slower than a clock on your desk because the floor is closer to the center of the earth and deeper in the gravitational well. The difference is tiny, billionths of a second over a lifetime, but it is real and has been measured with atomic clocks. GPS satellites in orbit, 20,000 kilometers above the surface, run faster than ground-based clocks by about 38 microseconds per day. If this were not corrected, GPS would accumulate position errors of roughly 10 kilometers per day. Time is not universal. It is local, and the rate it passes depends on where you are and how fast you are moving. Now take the direction of time. You think time flows from past to future, and that this direction is built into the laws of physics. It is not. The fundamental equations of physics, Newton's laws, Maxwell's equations, the Schrödinger equation, Einstein's field equations, are all time symmetric. They work identically forwards and backwards. If you film a billiard ball collision and run the film in reverse, the reverse sequence is a perfectly valid physical process. The only reason the macroscopic world distinguishes past from future is the second law of thermodynamics, the tendency for entropy to increase, for disorder to grow, for ice to melt rather than spontaneously freeze. And the second law is not a fundamental law. It is a statistical tendency. It says that systems tend to evolve toward more probable configurations. A shattered glass is more probable than an intact one because there are vastly more ways to arrange molecules in a shattered pattern than in an intact pattern. The arrow of time, the fact that eggs break but do not unbreak, is not written into the laws. It is a consequence of the universe having started in an extraordinarily low entropy state and of our living during the long statistical drift toward equilibrium. If the universe had started in a high entropy state, there would be no arrow, there would be no past and future, there would just be chaos in every direction. Now take the reality of the present. You think there is a now, a moving boundary between past and future, a moment that is real in a way that other moments are not. Special relativity destroys this. The relativity of simultaneity means that different observers moving at different velocities disagree about which events are simultaneous. There is no universal now. The present is as subjective as here. You would never say here is more real than there, but you feel instinctively that now is more real than then. Physics says both intuitions have the same status. Now is a perspective, not a property of the universe. What remains in Rovelli's framework is not a flowing river of time, but a web of correlations. Things are correlated with other things. A clock reading is correlated with the position of the sun. A memory in your brain is correlated with the previous state of the world. These correlations are real, but they do not require time to flow. They do not require a now that moves. They just exist as part of the structure of a timeless space-time. Time, in this view, is like temperature. Temperature is not a fundamental property of individual atoms. An individual atom does not have a temperature. Temperature is a statistical quantity that emerges when you average over large numbers of atoms. It is real in the sense that you can measure it with a thermometer, but it is emergent, not fundamental. Rovelli is saying that time is the same. It is a macroscopic quantity that emerges from underlying timeless physics, shaped by the second law of thermodynamics, a thermometer reading of a universe that does not, at the deepest level, possess the thing being measured. Julian Barber reached the same conclusion by a different path. In his 1999 book, The End of Time, Barber argued that reality consists of what he called nows, perfectly static configurations of the universe. Each now is a complete arrangement of all particles, all fields, everything that exists, frozen in a single instant. These nows exist in a vast abstract space Barber calls Platonia. Time does not flow through Platonia. Each now simply is. Certain configurations contain structures that look like memories, like records, like fossils, like tree rings, like geological strata. These internal structures create the appearance of a history, but the appearance is all there is. No time passed between the now that contains a dinosaur fossil embedded in rock and the now that contains you, standing in a museum looking at that fossil. Both nows exist. The relationship between them is structural, not temporal. The Big Bang is not an event that happened 13.8 billion years ago. It is a special configuration in Platonia, the one Barbour calls alpha. The idea that it happened, that time has been passing since, that billions of years of cosmic evolution led from that initial fireball to you sitting here, is exactly the kind of illusion Gödel identified in 1949. There is a now that contains primordial plasma, and a now that contains galaxies, and a now that contains you reading this sentence. They are all equally real. The ordering you impose on them, the unshakable feeling that the plasma came first and you came later, is a feature of the now's internal structure, not a feature of time flowing between them. You might want to reject all of this. You might want to say that physics has gone off the rails, that time is obviously real, that you can feel it passing right now as you take in these words, and that no equation can overrule direct experience. You would not be alone. The physicist Lee Smolin, in his 2013 book Time Reborn, makes exactly this argument with considerable force. He insists that time is real, fundamental, and irreducible. He argues that physicists have been seduced by the beauty of their timeless mathematical models into confusing the map for the territory. That a timeless equation does not prove a timeless reality, any more than a still photograph of a river proves the river does not flow. The debate between Smolin and the block universe camp, between presentists who believe only the present is real and eternalists who believe all times are equally real, is genuine and unresolved. Serious, brilliant physicists disagree. But here is what the evidence actually looks like when you stop being diplomatic about it. In favor of time being fundamental, you have Smolin's philosophical arguments, the raw force of human intuition, and a handful of speculative approaches to quantum gravity that try to restore time to the fundamental level. In favor of time being emergent or illusory, you have Gödel's exact solution to Einstein's equations and his unrebutted 5-step philosophical argument. You have Einstein's admission that he could not refute it. You have the Wheeler-DeWitt equation and its complete absence of a time variable. You have Rovelli's thermal time hypothesis, deriving the appearance of time from statistical mechanics. You have Barbour's timeless quantum cosmology. You have the Rietveld-Putnam argument from special relativity alone. You have 7 decades of closed timelike curves appearing in solution after solution of Einstein's equations, resisting every attempt at elimination. You have a chronology protection conjecture that has gone unproven for 33 years. That is not a balanced debate. The intuition that time flows is universal and compelling. But intuitions have been wrong before. The Earth feels flat. The Sun appears to orbit the Earth. Objects at rest appear to be in a fundamentally different state from objects in motion. Every one of these intuitions was overturned by physics. The intuition about time may be next. 3 routes, 3 completely independent intellectual traditions. Classical general relativity, through Gödel in 1949. Quantum gravity, through Wheeler and DeWitt in 1967. Thermodynamics and statistical mechanics, through Rovelli and Connons in 1993. 3 different starting points, 3 different mathematical frameworks, 3 different groups of researchers who were, for the most part, not thinking about each other's work. Gödel was thinking about the philosophical implications of Einstein's equations. Wheeler and DeWitt were trying to quantize gravity. Rovelli was trying to understand why time appears in a fundamental theory that does not contain it. And all 3, following their separate paths through entirely different terrain, arrived at the same destination. Time is not a fundamental feature of reality. The flow you experience is not a property of the universe. It is a property of you. The philosopher Hilary Putnam saw this coming as early as 1967. Using only special relativity, without any of the machinery of general relativity or quantum gravity, he argued that all events, past, present, and future, must be equally real. His conclusion was stark. Aristotle was wrong. At least he was wrong if relativity is right. Roger Penrose illustrated the same point with what he called the Andromeda paradox. 2 people walking past each other on a street, moving at slightly different velocities, have different present moments in the distant Andromeda galaxy. For one of them, a fleet of alien ships is still being debated by a war council. For the other, the fleet has already launched. The events are separated by several days of Andromedan history, yet both observers are standing on the same sidewalk a meter apart. If the present is objective, both of those distant moments must be equally real, which means the past and the future, at least in Andromeda, are equally real right now. The concept of a universal now that sweeps forward in lockstep across the cosmos cannot survive the relativity of simultaneity. Gödel's contribution was stronger than Putnam's. Putnam used the kinematic structure of special relativity. Gödel used the full dynamical equations of general relativity applied to physical matter distributions, and showed that the concept of time itself, not just simultaneity, but the entire notion of temporal ordering, fails in certain perfectly valid universes. The cosmic time that rescues the present in standard cosmological models, the preferred time coordinate defined by the expansion of matter, is not a fundamental feature of the laws. It is a contingent feature of our particular universe's matter distribution, an accident of initial conditions. Einstein sensed this before Gödel proved it. He told the philosopher Rudolf Carnap that the experience of the now means something special for man, something essentially different from the past and the future, but that this important difference does not and cannot occur within physics. He called it a painful but inevitable resignation. Gödel would not have used the word resignation. He would have used the word proof. January 14, 1978. Princeton Hospital, New Jersey. A man sits in a chair. He weighs approximately 65 pounds, 29 kilograms. His frame, never large, has consumed itself. His cheeks are hollow. His wrists are barely wider than the bones inside them. His name is Kurt Gödel. He is 71 years old. He has not eaten properly in months. His wife Adele suffered a stroke in late 1977 and was hospitalized for several months, unable to come home, unable to perform the one function that had kept her husband alive for decades. She could no longer prepare his food. She could no longer taste it first. And without her, he would not eat. Not because there was no food, not because nobody tried. Friends brought meals. The Institute arranged assistance. Nurses offered everything they could think of. Oscar Morgenstern, who had watched Gödel's deterioration with growing horror over the previous years, made desperate attempts to intervene. He had been receiving phone calls from Gödel, sometimes 2 or 3 a day, at all hours of the night. Calls filled with elaborate fears about poisoning, about forced institutionalization, about conspiracies that were internally logical and externally deranged. Morgenstern himself was dying of prostate cancer during this period. He would die on July 26, 1977, 6 months before Gödel. In his final months, even as his own body was failing, Morgenstern devoted significant energy to trying to arrange help for Gödel. He contacted the Institute. He contacted other friends. He made notes about Gödel's condition with the meticulousness of an economist compiling data. Perhaps because compiling data was the only response he had to a situation that had no solution. He recorded that Gödel was taking a wide range of medications for ailments he did not have. He recorded the phone calls. He recorded finding Gödel hiding in the cellar behind the furnace, and the shock of encountering one of the most formidable minds in human history, crouching in a basement, terrified of threats that existed only inside that mind. A nurse named Elizabeth Glinker later testified about Gödel's final months. His typical daily intake was a single egg for breakfast, plus a teaspoon or 2 of tea, and sometimes a little milk or orange juice. For lunch, she recorded, he generally had string beans, never meat. When they persuaded him to eat carrots, she called it a real breakthrough. Think about those words for a moment. A real breakthrough. Applied to getting a 71-year-old man to eat a carrot. He had been awarded the National Medal of Science in 1974, the highest scientific honor the United States government can bestow. He refused to attend the White House ceremony, even when offered a private car and an escort. He was elected to the Royal Society, the National Academy of Sciences, the American Academy of Arts and Sciences, the American Philosophical Society. Honors accumulated around him like light spiraling toward a singularity. None of them could penetrate the event horizon of his illness. Einstein had died on April 18th, 1955. That loss hollowed Gödel in a way that no subsequent event could match. The walks stopped, the conversations stopped. The one person at the Institute who engaged with Gödel as an intellectual equal, who took his ideas about time and reality seriously, who could follow the full arc of his reasoning without flinching, was gone. In the 23 years between Einstein's death and his own, Gödel became progressively more withdrawn, more fearful, more trapped inside the logic of his paranoia, a logic as airtight and as disconnected from reality as any formal system he had ever studied. The death certificate read, "Malnutrition and inanition caused by personality disturbance." John Dawson, Gödel's biographer, wrote what stands as the most precise epitaph a logician could receive. Unable to escape from the inner logic of his paranoia, to adopt, as it were, a meta-theoretical perspective, he succumbed to starvation in the grip of his obsessive fear of being poisoned. Like the actions of an inhabitant in one of those timeless universes he had envisioned, his death was, and was not, of his own volition. There is something in that sentence that the equations cannot capture. The man who proved that formal systems contain truths they cannot reach died trapped inside a formal system of his own mind's construction, unable to step outside it. The man who proved that the passage of time is an illusion ran out of time in the most visceral way a human being can. And the proof he left behind, the one that Einstein validated and the physics community sidestepped, has been sitting in the literature for 77 years, confirmed by independent developments in quantum gravity and thermodynamics, waiting for someone to take it seriously. The philosopher Paleograu called the neglect of Gödel's work on time one of the greatest scandals of modern intellectual history. He argued, in his 2005 book, A World Without Time, that Gödel's rotating universe and its philosophical consequences had been systematically ignored by both physicists and philosophers. Physicists ignored it because it was philosophy. Philosophers ignored it because Gödel was just a logician. And the result, perhaps the most consequential result about the nature of time since Einstein's own work, fell through the gap between disciplines and lay there for half a century, gathering dust in volume 21 of the Reviews of Modern Physics, while the intellectual world moved on as though it had never been published. Paleograu described the friendship between Gödel and Einstein as an association no less remarkable than the friendship of Michelangelo and Leonardo, if such had occurred, and argued that it produced a result that physics has spent decades trying to escape. That escape attempt has taken many forms: the observational dismissal, the chronology protection conjecture, the reclassification of Gödel's work as a mathematical curiosity, the subtle but persistent refusal to engage with the philosophical transfer argument that is the actual heart of Gödel's contribution. None of these attempts has succeeded. The proof stands. The equation has been written. The mechanism has been identified. And the physics community continues, to this day, to teach general relativity without mentioning that its own equations contain the proof that time is not fundamental. Students learn the Schwarzschild metric, the Kerr metric, the Friedmann equations. They do not learn the Gödel metric. They do not learn the five-step argument. They do not learn that the greatest logician of the 20th century used the most successful theory of gravity to prove that the most basic feature of their daily experience is an illusion, and that Albert Einstein confirmed he could not refute it. You feel time right now. You feel it in the way the words on this screen seem to arrive one after another, in the way your attention moves forward, in the way this sentence seems to be happening in the present, while the sentence before it has already slipped into the past. This feeling is the most fundamental aspect of your conscious experience. Without it, you would not recognize yourself. Without it, experience itself might not be possible. And the equations that describe the universe, the same equations that predict the orbital decay of binary pulsars to 14 decimal places of accuracy, that told us exactly when and where to point LIGO to catch gravitational waves from merging black holes a billion light years away. Say that feeling is not picking up a real signal, that the flow of time is not a perception of something out there. It is a construction in here, inside your skull, generated by the thermodynamic accident of being a macroscopic being with incomplete information about the microscopic state of reality. That past, present, and future do not happen in sequence. They coexist, that you are not traveling along a timeline. You are a pattern, a static pattern, embedded in a four-dimensional block of space-time that has no flow, no direction, no now, that sweeps forward like a searchlight. The feeling that you are reading this sentence right now is the same kind of illusion as the feeling that the earth is flat. It is compelling, it is universal. Every human being who has ever lived has experienced it, and it is wrong. 3 lines of evidence. Gödel in 1949, Wheeler and DeWitt in 1967, Rovelli and Incompleteness in 1993. 80 years of convergence. The proof stands. The equation has been written. The mechanism has been identified. And Hawking's attempt to make the universe safe for historians remains, as of today, exactly what it was when he published it in 1992. A conjecture, an unproven hope dressed in mathematics and delivered with a joke about tourists from the future. Gödel knew this. He knew it when he walked with Einstein in the autumn light of Princeton, 2 exiles from the old world discussing the deepest properties of the new one they had discovered inside the equations. He knew it when Einstein died and the walks ended and the silence closed in. He knew it when the physics community filed his result away and changed the subject decade after decade, as though a 75-year-old proof about the most basic feature of human experience could be made to disappear by not mentioning it. He knew it in the cellar, behind the furnace, hiding from threats that existed only in his mind, a mind that could see further into the structure of reality than almost any mind that has ever existed but could not see its way out of its own terror. He knew it when he stopped eating. He knew it when they wheeled him into Princeton Hospital for the last time. He weighed 65 pounds when he died. The proof he left behind weighs more than the physics community has been willing to carry. It has been sitting there in volume 21 of the Reviews of Modern Physics, pages 447 through 450, for 77 years. 4 pages. It has never been refuted. It has been independently confirmed twice by developments in entirely different branches of physics that Gödel never lived to see. And you, sitting here right now, feeling time pass as you take in these words, were never told about any of it. Gödel knew. Einstein admitted it. And nobody told you. The question they left behind is the same question that hung in the air between them on those walks along Mercer Street in Princeton, between two old men who had seen further into the nature of reality than anyone wanted them to look, and who found there something that could not be unseen. If time is not real, then what is happening to you right now?